Chapter 12, Section 11, Modelling with Differentiation, is one of the trickiest parts of this book to explain because it's one where you really do have to use a bit of intuition, a bit of sense. And so my first bit of advice is, if you're not finding this section easy, you need to develop your intuition. You can develop your mathematical intuition and your intuition for differentiation questions, and the way you do it is go back, look at the earlier parts of this chapter. Don't try and do this if you don't know the other parts of the chapter well, okay? So immediately, if you know there's a bit of a gap where you haven't thoroughly learned everything in sections 1 to 10 of this chapter, stop the video, don't even try and do this part of it, go and learn those things thoroughly first, and then come back to here, okay? Now, a couple of other bits of initial advice before we stop and look at a particular question. First of all, if you've got dy by dx, that means the rate of change of y with respect to x, okay? So if I don't have a y and an x, if I have a v and an r, or a v and an x, as I do in this example 22, or let's have a look at the question, I've got a theta and a t, d theta by dt just means treat theta like the y, treat t like the x, okay? So the letter that comes down here, downstairs after the d, that's the thing you're differentiating with respect to. So that's the thing you are treating as though it was the x. So here, when I've got t squared minus 3t, the t is the thing that the power is a 2, so when I differentiate it, I bring the 2 down to the front and reduce the power by 1. So 2t minus 3 is the derivative of t squared minus 3t. So if that's theta, this is d theta by dt. Okay, maybe that seems obvious. I don't know. I remember when I learnt this, that didn't seem obvious. We'd done a whole chapter. I'd spent a couple of weeks working in differentiating with respect to x, and suddenly I was differentiating with respect to something else, and I never really understood what with respect to meant until somebody put it in those terms. It's just the thing that you treat as though it was the x. Okay. And the thing on the top is the thing you treat as though it was the y. So if there's a t to the power of 2, then pretend the t was the x, bring the 2 down to the front, deal with it that way, okay? That's the first thing. And that means if you have anything, so here I've got a formula that it relates p to r. I haven't even read the question, I don't know what p is, I don't know what r is, but I know that if I wanted to, I could find dp by dr, okay? We have a method for finding that. In this chapter, in this exercise, all of the questions are in context, but they don't have to be in context for this particular element of it. If you have a formula that links p and r, that gives you p on its own as the subject of the formula, and r is the thing on the other side of the formula, there's an expression in terms of r, you can find dp by dr by differentiating with respect to r, okay? What that then means is a separate question. But first of all, just be aware that you can do it, okay? So, for example, I'm looking at this one here. I've got a formula which links a v and an x, so I can find dv by dx, okay? I don't have to worry, if all I want to find is dv by dx, I don't even have to worry about what that means. Obviously, from the question, I've got a big 3D shape here. This is probably a volume, and x, it looks like, is one of the lengths. But if you just want to find dv by dx, you can switch off the context. You don't have to worry about the context. You just do the differentiation. Okay, so that's the first thing. Don't worry about the notation. If you get any two variables linked, you can find dA by dr, dP by dr, theta by dt, whatever it happens to be. Okay, that's the first thing. Now the second thing is actually putting that context in there. Then, so what does a derivative mean? So dy by dx means first thing to get in your head is it's a rate of change. A derivative is a rate of change. So it's the way that y changes for every unit of x changing. Okay, that's what a gradient is, isn't it? If I've got a gradient of 2, then that means if I make a 1 unit step in the x direction, I'm making 2 unit steps in the y direction. Okay? And when I say I've got a gradient of 2, we're perfectly comfortable with the idea that the curve can have a gradient of 2 here and a gradient of 4 here, even if the gap between here and here is only a unit gap, right? So I don't mean that I stand on the curve there, I take a step to the right and I move 2 steps up and then I'm back on the curve. I might not be. what I mean is the gradient of the tangent to the curve at that point has a gradient of 2. Okay, if I say the gradient is 2, that's what that statement means. So dy by dx is the rate of change of y with respect to x. If you find the rate of change of y with respect to x and it's a curve, then you can find the gradient at one particular point on the curve for one particular value of x. That is the way in which y, the rate of change of y with respect to x at that point. That means that if I make a unit change in x at that point, how would y change? That's what dy by dx would tell us. Except that if we actually literally did make a unit change in x, the gradient would have changed as well because it's a curve. Okay? So that's the sort of double thing that we're trying to do here. We're saying dy by dx tells us a gradient. That tells us if there was a unit change in x, how much of a change in y would there be? And we remember that actually, if we did change x by as much as a whole unit, if x increased from 3 to 4, then the gradient would change. But what we mean is, what does the gradient, what does the tangent do? Okay? So that's what we mean by dy by dx. So what about things like dp by dr? Well, that's the same thing, only every time I said y, change it for a p. Every time I said r, change it for an, every time I said x, change it for an r, okay? So, in order to put it in context, we need to understand that's the idea, it's a rate of change. We also, before we can put these in context, probably the most important part of this section, if you are asked now for a maximum or a minimum value of anything, you think of differentiation. A maximum and a minimum value, well, maximums and minimums are examples of stationary points. If you put the first derivative equal to 0, that gives you a stationary point. It might be a maximum, it might be a minimum, it could be a point of inflection. But if you're asked for a maximum value, find the stationary points. If there's more than one stationary point, then maybe some of them are maximums, some of them are minimums, but find the one which is a maximum. If you're asked for the minimum value, find the derivative, put it equal to 0. So whenever you hear the words maximum or minimum in relation to some sort of function, your head now says differentiate. Put the derivative equal to 0. That is how I find the stationary points. Stationary points quite often are maximums and minimums. And then you need to look at the context, okay? So, for example, I'm just looking at the first question here. I can differentiate and put the derivative equal to 0 and find a stationary point. Would I then need to find the second derivative in order to classify that stationary point? No, because this is a quadratic. So if it's a quadratic, I know that it's only got one turning point, and I know from the coefficient of the t squared that it's going to be a U-shaped quadratic. So that one turning point would be a minimum because it's a quadratic. Now, if you're in an exam, you can't just say, well, I found a turning point, so it must be a minimum. You say, I found a turning point, and it is a minimum because, and then justify it one way or the other. So if you liked finding second derivatives, you could find the first derivative, you could find the second derivative, you could prove it's a minimum that way. Or you could find the first derivative and say, well, because it's a quadratic and blah, 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 everything I just said, that's why it's a minimum, there's only one turning point. Okay, so maximums and minimums, rates of change. Let's get those two things in our heads, okay? Now, let's finally get back to an example. Now let's try and put things in context. So if we have the volume of a sphere equals 4/3 pi r cubed, well, we can, if we want, find dv by dr, because I've got a formula that links a v and an r. Don't have to even ask what it means yet, but it is 12/3 pi r squared, which turns out to be 4 pi r squared. Okay, so the rate of change of volume with respect to radius is 4 pi r squared. What does the rate of change of volume with respect to radius mean? It means that if you had a sphere that was increasing in size, the way if you increase the radius, this tells you about the way the volume increases as the radius increases, okay? So for example, if I pick r equals 3, then dv by dr is 4 times pi times 9. So 4 times 9, so 36 pi, okay? Which is, roughly speaking, you know, it's 36 times 3 and a bit. So should we call it about 110-ish? Okay, approximately 110, right? So that means if when r equals 3, if the radius were to increase by 1 unit, the volume would increase by 110 units at the point when r equals 3, okay? Now, if r actually did increase from 3 to 4, the dV by dr would now have changed, and it wouldn't be at 110 anymore. But what we mean is, at the point when, if you increase the radius from 2 to 2.5 to 2 3/4 to 2.9 to 2.95 to 3 to 3 and a bit to 3 and a little bit more to 3.5, at the point when the radius goes through 3, the volume is increasing this much, okay? You could look at r equals 3.1 and 3.2 and 3.3, and you can see how the rate of change of volume changes as well if you wanted, okay? So that's the idea. dV by dr tells us what happens to the volume as you're changing the radius. It tells us what happens to the volume as you're changing the radius at any particular value of the radius that we care to choose, okay? The way to think of it as a unit increase in the radius would affect the volume in this way, except we have to do this little double think that if we did genuinely have a unit increase in the radius, then the volume, by the end of that change of your unit, the volume wouldn't be increasing this way anymore. Another way to think of it, I suppose, would be your speed at a certain instant, right? But maybe that will help if you're struggling so far. So if I say I'm going at 30 miles an hour now, but I'm then increasing my speed up to 40 miles an hour, there may be only a split second where my speed is actually 35 miles per hour, but you understand what I mean to say that I've got to go through 35 miles per hour. I don't stay at 35 miles per hour just because the time unit is 1 hour. I don't stay at 35 miles per hour for an hour and then increase after that. I may only be at 35 miles an hour for a split second, but we understand the idea of 35 miles per hour for a split second. In the same way, the rate of change of volume with respect to radius is 110 at the point when r equals 3. Okay, at that particular instant, and instant's the wrong word because we're not measuring time, we're measuring radius, but at that particular point, that's the rate of change of volume with respect to time. Okay, so taking all that together, we can answer questions along these lines. So let's have a look at example 22. We've got a large tank the shape of a cuboid made from sheet metal, and it has a horizontal base and no top, and it's x meters. The height of the tank is x meters, and two opposite faces are squares. Okay, so far we've got this in our heads. We've got a square here, we've got a square at the other end. It's y meters long, and the volume is v. So, and just to avoid confusion, the y is just some length. Okay, we're introducing a y because we've got a length that we don't know. Show that the volume of the tank is given by this. Well, there's no differentiation in this. There is no, sorry, example 22. Show the volume of the tank is given by this. There is no differentiation involved in this bit. This is just think about the tank. And the way that we do it, and this is common to a lot of the questions, if it's a volume involved, well, we could think about surface area, we could think about volume. And if we write those two things down, we can get volume in terms of x and y. We can get surface area in terms of x and y. And if we take those two equations and eliminate the y, we can get volume in terms of x. Okay? Similar to these questions over here, we've got a flat shape, so I can think of perimeter, I can think of area. If I get perimeter in terms of some different variables, if I get area in terms of some different variables, and I eliminate the one that I don't want, so example 10 is a good example. Look, there's an x here, there's a y here. Get the length of all these lines, get the, what is this, it's wire, so get the length of all the wire in total in terms of x and y. Get the area that this covers in terms of x and y, and then you can eliminate the y. You've got two equations, and you can eliminate one of the variables, okay? So that is a common first step, but doesn't actually have anything to do with differentiation yet. So, given that x can vary, use differentiation to find the maximum. There we look, maximum, minimum. When I say maximum, minimum, you think differentiation. So even if they hadn't said it, we need to find maximum, minimum value of v. So dv by dx, that's the thing that we can do. We've got v in terms of x, we can differentiate with respect to x. So dv by dx, if I want to find the maximum or minimum, I've got to put it equal to 0. When I put it equal to 0, I find two different x coordinates. When I find two different x coordinates, I substitute them in to the formula for v, and that gives me v coordinates, okay? Now, I've got x equals 3 v equals 36. Why did I discount the minus 3? Think about the context of the question now. X is a length, so it can't be minus 3. So I've got x equals 3, v equals 36. What we've done there is we've found a maximum value of v, and we never had to really stop and think about what we mean by dv by dx, did we? We had v in terms of x, we differentiated, we found the x coordinate, we substituted in the x coordinate, we got v, so we got a maximum value of v, okay? What it actually means is, if you make x equal to 3, then that's going to maximise your volume, given the rest of the conditions in the question. So if you've got a cuboid made from 54 metres squared of sheet metal, and you want the maximum possible size of tank out of that sheet metal, then the way you do it is you let the square, and you want the square at the end, then you let the square at the end be a 3 by 3 square, okay? How do we know it's a maximum? That's part C, look, justify that the value you found is a maximum. Well, we could justify it by thinking about the cuboid. If I wanted this to be a minimum, then I could make x as small as possible. I can have a really, really tiny x and have a really, really tiny little square on the end, and a very, very, very long, thin cuboid. And if you imagine that x becoming smaller and smaller and basically getting to be 0, then x equals 0 would give x equals very, very tiny would give a very, very tiny volume, wouldn't it? Couldn't actually have x equals 0, because then you can't use up the 54 meters cubed of sheet metal. But you might be able to justify it morally, sort of thing, in your head by just thinking about it. It can't be a minimum, can it? How do we know it's a maximum, though? Well, we know it's a maximum because it can't be a minimum, but really, if we're going to answer that in an exam, we're going to have to do what they've done here. Look at the second derivative, and the second derivative turns out to be negative, therefore it must be a maximum, okay? So the intuition as to what's going on in these questions, thinking about what dv by dx means, thinking about the rates of change of volume with respect to a length, difficult to get your head round, but when it comes to the actual questions, what happens in this example is fairly typical. Part A, quite tricky. You need to think of volume and area. We know about volume, we know about area. Write down a formula for area, write down a formula for volume. Use those two together to get rid of y. And remember, y was something we had to introduce ourselves in the first place. Bit fiddly, but there's no chapter 12 on that. There's no differentiation. It's just algebraic cunning, right? Part B and part C, it helps if you understand what dv by dx means. But all you really need to know is, if you're just bloody-mindedly trying to get the marks, all you really need to know is maximum or minimum value. That means find a derivative. What derivative can I find? dv by dx. Find the derivative, put it equal to 0, find the x value, find the v value that goes with it. When we've done that, is it a maximum? How do I justify that it's a maximum? Find the second derivative and use that. Okay? It's a fairly typical state of affairs that you can do a lot of these questions where you can think about the part A, the part B and C, where you've actually got to do the differentiation. You don't have to stop really and think about what it means. So I'm just picking one at random. Question 7. We've got V in terms of R. Find the maximum volume of the cylinder. I haven't even read the rest of the question, but V is obviously volume. If I want to find the maximum V, I'm going to differentiate. I'm going to find dV by dr. I'm going to put it equal to 0, find the R value, substitute that in and find the V value. I might then have to justify that that is a maximum, so I might have to put that into the second derivative. And I never really have to stop and think about what dV by dr means. Obviously it helps if I know what it means, but when it comes to the differentiation, it's just using the techniques really from the previous section. Part A might actually have some harder maths in it, but it's not a differentiation problem. I hope that helps. Very last thing, I know this is quite a long video now, very last thing I'd say on this section is that if you're feeling like it's difficult, nothing is going to help you so much as trying a few examples. Now you've had a watch of this video, you've got a bit of an idea of what I'm talking about. If it doesn't really make sense, stop, try a few examples. Like the first thing I said was this is really difficult to explain. That's one of the reasons I've been talking for so long, trying to make it make sense. But actually, the only thing that's really going to get it fully in your head is if you get stuck, you're not sure what to do, you try something else, and eventually you'll start getting the intuition for it, and that will help you. Good luck.